I'm really excited that you're all here with us, but before I turn it over to Dano, I wanted to say thanks to, for posterity's sake, I suppose, but thanks to all of our sponsors and thanks to the team who put all of their effort into organizing a wonderful conference. So I'm going to tell you a little bit about Dano Weisbord, who is the Chief Sustainability Officer at Tufts. Dano, I'm really sorry, but I have your bio
No rush.
right here.
All the time in the world.
Yeah, okay, here we are. So you joined Tufts just last year. And so Dano is working with senior leadership to further Tufts' commitment to be a higher education leader in sustainability and climate matters. He's working across the university to bridge campus operations with education, co-curricular, and research activities. Dano came to Tufts from Smith College, where as Associate VP for Campus Planning and Sustainability, he was responsible for the electrification and decarbonization of a thermal and electric district energy system. Previously, Dano advised on corporate environmental responsibility strategy and consulted across higher education, energy, international NGO, mining, and real estate sectors. A lot of sectors, Dano. And lastly, Dano is also a jumbo and has a Master's of Arts in Urban and Environmental Policy and Planning from Tufts. So, Dano, over to you. Thank you for being here.
Thanks. Thanks. This is like the small and committed crew. So thanks. So I think we'll do a couple things. I'm new. I'm in month 4. So I think I'll just start with a little bit of background about me, and then I'm really going to talk about electrification of the campus. And this is such a small group. But I'm just going to invite you to and I've even almost met everybody since as you came in. So I have a good sense of who's in the room. But I will actually, invite you to just stop me and we can chat as I go. So if there are things that you see or questions that you have, just raise your hand and we'll just do this as we go along, because we can do that in a small group and that's more fun, honestly. And it really is more like a conversation. So just, uh-oh. Cool. So just a little bit of background on me. From 2010 to 2014, I lived with my family in the United Kingdom in London, and I was working for an international aid and development organization. And I'm also kind of a history buff. And living in the United Kingdom, if you're into history, is a very rich experience. There's a lot of stuff going on. So just very quickly, this is an energy conference, and so who's talked about Watts today, right? So and the story of Watts. They were named after a guy, James Watt, and he made this thing, right? This is the oldest existing Watt and Boulton steam engine from 1777. And Watt didn't invent the steam engine, but he improved it a lot, big time. It was a pretty inefficient device before that. So here we have, this is in the Museum of Science and Technology in London. It's the Watt and Boulton steam engine. Okay, on the left side of the chart is a map that was drawn in 1815 by William Smith. He drew the first map of the subsurficial geology of Britain. So what that told them was where the coal was. So the black things on the map are the coal veins in Britain. So we take two things, right? We take a device that takes fossil fuels and makes it into work really efficiently. And we take a map that says, here's how I can get the fossil fuel really efficiently. And now these are the primary ingredients to the Industrial Revolution, right? Which is entirely a fossil fuel based thing. And the interesting thing about that, right? If you think back on who's seen one of those charts that show the concentration of CO2 in the atmosphere, right? And the thing goes up, right? This is where it started, right? Because it wasn't until we were taking all of these veins of coal, right? Which is really ancient, really, really old biomaterial that's been sequestered underground and liberated that into the atmosphere. We weren't rapidly building up concentrations of CO2 in the atmosphere. So this created the Industrial Revolution. The Industrial Revolution improved the quality of life for humans all over the world, but did so in a way that was not consistent, right? So there we go. Okay. As I mentioned, when I was living in the UK, I was working for an international aid and development organization, hey there, which worked in 47 countries. This was a photo I took, a group of women that I met in far north Vietnam, in a village called Lai Châu. And they were dealing with significant food insecurity. And a lot of that food insecurity had to do with change in weather patterns. And the change in weather patterns in this community meant that the traditional knowledge, thousands of years worth of knowledge, was becoming less useful because the weather patterns were changing in ways so that when to plant and when to harvest was becoming chaotic. And so that's like, that's, you know, what we're thinking about as well. We've got this industrial revolution. It improved the quality of life for people around the world, but it did so in a really uneven way. And the people who now today are the poorest are really suffering the consequences of that. So we really need to think about, it's right, the transition here is about how do we get away from fossil fuels? How do we think about that in ways that at a global scale, we are evening out and creating a more uniform set of benefits. So these are the things that are in the background. And so on the left, right, we have 8 billion people on the planet, rich and poor, and all of them want a better quality of life, right? Even super wealthy people, they say they want a better quality of life. And the dominant paradigm, right, the fossil fuel economy paradigm is better is more. Better is more stuff. So I need more energy, I need more fuel, I have more emissions to get my more stuff. And so to create better quality of life for everybody, and to do that in a way that that enables us to continue to live on the planet, that's the dilemma. That's the sustainability challenge. So as a wealthy country, as a wealthy institution in a wealthy country, we need to be thinking about how do we take what we have, how do we start to decarbonize it? How do we start to, how do we stop emitting the stuff that's actually hurting all of us and hurting us ununiformly? Okay, here we are at Tufts, 3 campuses, rural, suburban, urban. So I thought I'd talk a little bit about the process of electrification. And I'll give a little bit at the update, a little bit of an update where we are as Tufts institutionally, because we're in a really interesting moment here. And in general, I thought I would pitch this as like, here's kind of how who's heard the word electrification? Who like really like, be honest, like, do you really know what it means? Would you know how to do it? Okay, great, good, 1, excellent. Chris, you're pretty good, I think.
Yeah, a couple things.
Yeah, you know some stuff. So I'm gonna try and give a little bit of a 101. So if you know the 101 stuff, like, you know, hopefully I'll be entertaining, but otherwise, hopefully this will be useful to you. And again, stop me at any point. Very quickly, here's Tufts. This is one view of Tufts' carbon footprint. So the bar all the way on your left is the CO2 that we measure. I know some of you've been working in the class, right? So we measure emissions that come from our operations, which really are buildings and that Fleet Plus piece right there in the middle. Things above that are things that are in our supply chain, stuff we buy, stuff like air travel, materials, construction, food. And that one fades out because we collect some categories of information of our supply chain, but we don't do it in its totality. I'd like to get to the point where we are being more fulsome in terms of looking at our whole supply chain, primarily because I think there's really good opportunities in our supply chain for reduction. So that's something to think about, but that's why that one fades out. Within our operations, the vast majority of our CO2 emissions are associated with buildings. And you can even see that. And then, so under the dotted line, Grafton, Boston, Medford, you can see the different campuses and the rough proportions. And here in Medford, you can sort of see East Campus, that's the athletic area, lower campus, upper campus. They're actually, we think roughly comparable. So that's kind of our emissions. That's kind of our emissions profile. And it's why we kind of have this priority around buildings and building electrification as like the #1 thing. It's our single largest source of emissions, and it's a critical challenge everywhere. So we're going to do the quick overview of kind of like, okay, so you got some buildings, where's that emissions coming from? There's really two things, and there's really kind of only two big things. It's heat and electricity, right? So heat, heat, here's what's incredible, right? Anywhere, all cold climates, we're still doing the same thing that we've been doing for thousands of years, which is we just light a fire. The fire happens to be in a box somewhere else. It's in a basement, it's in a boiler plant, but it's just an open flame in a box. Setting stuff on fire is a really good way to make things warm. Setting fossil fuels on fire is awesome because they're full of energy, right? They have really bad side effects, but they're really energy rich. So heat is one of our key sources of CO2 emissions. The other one is electricity. Now, electricity, for the most part, the majority of electricity around the world is kind of made the same way. I've got an open flame, I'm burning fossil fuels, I'm boiling water, I'm making steam. The steam is pushing on a set of turbine blades. It's making something go around and around, and I'm rotating magnets and copper against each other. I'm getting a current. Right? What's important here is I've got rotational force. That rotational force is coming from the ignition of fossil fuels. So that's my carbon emissions, is from that open flame. Everybody with me so far? Okay. So electricity, I can imagine a way that we can deal with electricity, right? There's some combination, like it's not easy, it's not simple. This is a vast oversimplification. If you saw, we're on the panel around wind energy, you got the complexity, right? But we can imagine a world in which we're like, okay, I could get electricity from wind turbines and solar panels and maybe some other stuff. There's like I've got some nuclear in there, I've got some hydropower in there, but I've got these no CO2 tailpipe emission sources, right? So if I can just use electricity for everything, I can imagine a world where I've got a zero carbon electricity system, right? And electricity, now I just want to mention, right, cooling is the other big thing we do on a campus, but cooling is generally run on electricity. So that's why it's in my electricity box. Okie doke. Right. So the real problem is heat, lighting stuff on fire. And currently the way we do heat is like, it's like choo-choo train technology. We're just lighting stuff on fire in a box. And we're like using all this heat energy and we're trying to contain it. And we're trying to make it do stuff for us, provide energy services to us. Instead, we could be thinking about it. We should be thinking, instead of the train, we should be thinking of the refrigerator. What's the refrigerator do? How does the refrigerator work? It's a heat pump. Thanks, Chris. It's a heat pump. Right? Does anybody, like, does a refrigerator make heat? Yes. Where's the heat, Tina?
It comes out the back.
There is heat coming out of the back. Do you know where that heat's coming from?
The inside.
Yeah, it's coming from the inside. So is it making heat or is it just moving heat? It's moving heat, moving heat. So here's an electrical device, right? And it's got a widget in it that's taking heat from the inside and moving it to the out. Window air conditioner, same thing. Plug it into the wall. It moves cold air from the outside in. I can go into how one of these things works if you're interested, or I can sort of gloss over that and you can just trust me for the physics. Not getting a feel for this. Let's just say, right, it's a device and it has a working fluid inside, and at one side it's hot and one side it's cold, and that hot and cold is happening through change in pressure. Right? When I pressurize something, it gets hotter. And when I let that pressure go, it gets cold, right? And by moving a fluid around in a circle through that system, just pumping it, I get hot and cold. And if I put a really cold pipe into a refrigerator, right, the slightly warmer air inside the refrigerator is going to warm up the pipe, right? And that heat is going to travel around and go outside. So you could actually heat a room with a window air conditioner if you turned it around. It's not a real good way to go. It's super inefficient, but you could do it. Again, not well, you might freeze. Okay, here at Tufts, we are in a district environment, right? We have lots of buildings, and rather than having, and this is how most campuses work, college campuses, hospitals, retirement communities. There's lots of places that work in a district, most of Denmark. I mean, there's lots of places that work in a sort of a district context where you say, we're going to manage the heating and cooling of buildings across our whole portfolio, not just building by building. Because most people, it's like if you live in an apartment building, there's like a boiler and an air conditioner in the basement or on the roof. You live in a house, same thing. Here, we're handling it across the whole thing. So let's talk a little bit about how that happens. So how does that happen here at Tufts? Right, on the left, we have a power plant. Right, so we have boilers in a central plant. We're burning fossil fuels here. It's mostly natural gas, and we are making steam. That steam goes into pipes. So there's our Tufts power plant. This is the Smith College steam system being built in 1947. So like this is like old tech. Actually, and Smith had a steam system from 1896 as well, kind of, that was still functioning, right? So again, Industrial Revolution era tech. There's a little bit of hot water distribution here at Tufts as well. So sometimes it's coming as steam, sometimes it's hot water. The steam, you know it because you walk around campus and you're like, that's steam coming out of the ground, right? Don't touch that, it's really hot. Okay, and then it goes into buildings. And it goes into the buildings, and this is the most simple way that the heat goes into the building, is a radiator, right? It's like I get steam, it goes into the radiator, the radiator gives up the heat into the room, the steam cools off, it turns back into water, it goes back to the power plant, and it goes around and around again. In buildings like this one, it's a little bit more sophisticated. The steam comes into the building, it's usually heat exchanged for hot water, and it goes around and it comes through a ventilation system, right? There's fans like pushing over it, it's pushing it into the room. But it's all starting with a flame. Like there's a flame back in the power plant, it's heating everything up. So that's how we kind of do it today. So far, so good? All right, excellent. So how do we electrify? So to electrify, what we do in a district system is we have a plant, but instead of having a boiler, instead of having an open flame, we're gonna have a really big heat pump, a really big refrigerator. On the left, that's a heat pump. That's a ground source heat pump at Carleton College. That's heating and cooling most of its campus. And you have, instead of having steam pipes, and you have a lot of leakage from those steam pipes running underground, we have pipes like this. This is at Smith. This is new HDPE plastic pipes that are thermally insulated going into the ground. Right? And we're running hot water, 120 degrees, 130 degrees. Some campuses run them up to 160 degrees, but it's not high pressure steam. A lot of places, Tufts does low pressure steam, so it's like a little bit over 200 degrees Fahrenheit. High pressure steam, 360, 380, really hot. And then we have to deal with our buildings, and buildings are really difficult. So this is the chapel at Carleton College that they converted. So instead of heating it with steam, right? So when you've got something really hot, I don't need a lot of surface area to move that hot air into the room. I just need, right, a small surface area. I need a radiator. I need a bunch of radiators. And if you've got a chapel that's like a really old leaky building, it's stone, it's cold, it's damp, it's miserable, right? If you're going to heat that building with low temperature hot water, now I need a lot of surface area because the thing that I'm using to heat it is just a lot cooler. So this whole thing is a giant radiator, and it wraps all the way around the inside of the building. And they've successfully heated this cranky old stone chapel using low temperature water. That's actually a miracle, but that's actually really expensive. And it's the buildings part of this, not the plant, not the distribution, but the building renovations part. That's the really expensive part. So just hold that in mind. Yes.
Did they had more insulation in that case at all, or were they just adding the radiator around the base?
This is such an awesome question. So the question was, did they add more insulation in the building? And the answer is, in this case, I don't actually know, but let me tell you what I do know, which is when you have a campus like the Tufts campus, we have some really new, great, tight, highly energy efficient buildings like the JCC. And we have some really, really terrible old leaky buildings. And the problem is it's really expensive to go and insulate and air seal all of the buildings before you change over the system. So right, and we don't actually have enough time or enough money from a climate standpoint to renovate every single building and make it like as awesome as we would like to have it. So the challenge is, can we find ways to do this in buildings that are maybe not great and have it work and be good enough so that over time, as we do renovate these buildings, which we're doing anyway, we do the air sealing and we do the insulating. So the traditional kind of like the traditional approach to mitigation in a campus setting was like, we're going to do all of the energy efficiency stuff first, and then we're going to change the source. And I would say, I think that thinking is dead because it's too slow. Right. So we actually are going to like change the source, and then we're going to catch up with the renovations over time. And that takes a different kind of thinking and discipline than most campuses are ready for. It's like at Smith, where I was working previously, it took us a while to sort of like get our heads around that. Because everybody wants to renovate everything perfectly, because pride of place and stuff. Okay, this is, so just schematically, right? This is kind of what this looks like, right? You would have, here's a bunch of buildings. I've got a hot water loop. I've got a cold water loop. There's different ways of doing this, but let's just keep it at that for right now. I've got a heat pump down here, right? It's got a cold side and a hot side. And then the question is where am I getting the source, right? A refrigerator uses the air as its source. There are better sources. You can use the ground as your source. The ground is 55 degrees, 55, 60-ish all the time. So let's imagine it's a hot day outside and I've got a pump and I can run fluid through the ground and I can cool off some water to 55 degrees. And then I can run it back out here to my plant. I can put it in my cold water loop and I can have it come into this building, and it's already 55 degrees. So I can like run it through coils or equipment and I can like make it pretty cold. All I've done is pump water around. Right? I haven't lit anything on fire. Right? I'm just taking that cold temperature out of the ground and I'm pushing it into the building. Right? That's like not bad, right? So that helps. Right? That's why ground source is more efficient than air source, because air source, it's like, I want it cold in here, but it's 90 degrees outside, not 55 degrees. If it's 55 degrees, I just open the window. Right? This is the way that I'm just opening the window, except I'm kind of using the underground, right? Like I'm opening the window in the cave.
How actively managed is that? Or is it like a fairly like AI or like computer managed process? Or do you need some like a technician there pressing the button saying, okay, since it's so hot today, we need to make sure that the cold water does this?
So our campuses as they exist right now are highly managed.
Right.
All of the systems, all of the controls, all of the buildings, all the separate buildings actually report into a single kind of automated control system. And there are people who manage those controls. They look for alarms and it's like an active thing. And there's a lot of AI in it as well. So it's both of those things happening at the same time. This needs the same thing. For the people who I've talked to who are operating these systems, it's actually simpler and easier, and they break less because the temperatures and pressures are lower. When you have a high pressure steam system like we had at Smith College, stuff breaks all the time. The thing is just eating itself all the time, right? Because remember, like think choo-choo train technology, right? It's like high pressure, high temperature. It's harder to manage, but it's what we're used to managing. So we think, oh, this is going to be really hard to manage, right? But there's an upskilling and there's a labor force implications to this that are very real. So this is, people see this diagram and they're like, oh, well, if you do ground source geothermal, welcome. If you do ground source geothermal, like you're going to have this giant hole in the ground. No, it looks like this. This is the Carleton College geothermal field. Done, right? That's their main green. That's their geo field. So that's pretty cool. Yeah.
So I remember one was that geology department, Lane Hall is actually using the geothermal to cooling their system in summer, right?
Yeah, that's right. So at Tufts, we have one room in one building that's being geothermally heated and cooled. And it's Lane Hall. And if you go onto the like kind of center campus side of Lane Hall, you'll see there's one like well, and it's got like a red and white stick on it. And that's the geo well. So if you want to see what this looks like, you can go see that. Normally they don't leave the head of the well. That was a research well, so it's sticking out. Normally you just bury the whole thing. You don't see it. Oh, I'm sorry, Emma, you had a question.
Yeah, it was just whether or not Tufts has looked at what the actual geo well would look like and how deep the wells would be, and if it would be more of like a spread out shallow one or like or super deep.
Yeah, so there's different ways. Let's come back to this, but will you remind me? Because this is actually a fun question too. Okay, so just another thing to think about when we think about campuses and districts. This is actually this is an hour by hour chart of energy demand at Smith College. This is a real year. So that's a whole year going left to right. So it's January 1st all the way to the left, December 31st all the way to the right. When the arrows point up, it's heat demand. When the arrows go down, it's cooling demand. So all the red is heat, all the blue is cooling, and the purple is simultaneous. So there are times of the year, it's about, at Smith, it was about 20% of the hours of the year. So I would say like in the Northeast, in this region, about 20% of the hours of the year, a campus is needing heat and cooling at the same time. So this is really interesting. I got, right, in January, February, super cold, I've got a lot of heating demand. Here's where it gets hot. But all through this middle, I've got moments when it can be hot, when I've got hot and cold at the same time. Well, when you have a heat pump, right, you can just move that thermal energy from the hot pipe to the cold pipe. So if you have a dining hall that's full of people and it needs cooling, but you've got a dormitory that everybody's left and it's cold, right? You can take the heat out of the dining hall and essentially put it into the dormitory. It's not quite that straightforward, but in concept, that's what's happening in a district. So there's a lot of, like, the more diverse your district is, and campuses are great for this, the better, the greater sort of the efficiency potential you have. Okay, so that's what a campus energy load looks like. And so let's just talk about the benefits of this, right? If we can have a system, right, that is running on low temperature, and I've got hot and I've got cold, and I can deal with things simultaneously, and I can run this all on electricity. Here's what I've got. I've made the thing electric, and I can make that electricity carbon free. So now I've got a decarbonized heating and cooling system. I have efficiency potential. I'm distributing hot water instead of steam. I'm simply saving energy from doing that. How do you know that, Dano? I took this picture yesterday. Anybody recognize that location? Right, so why is there no snow on the lawn there? Yeah, that's where the steam line is. And in fact, you can see, you can't see it in this picture, but there's literally steam, right? There's steam coming out of this cover.
You can see it coming out of the vent thing on the left.
Yeah, you can see it coming out of there, right? So there's steam, and it's so warm that it's actually dried the pavement, right? And it's melted all the snow as the line goes across to there, right? So we know that's wasted energy, right? If we're melting the snow on the outside of campus, right? That's a waste of energy. So those pipes I showed you that are plastic, right? They've got a lower temperature, so there's less of a difference in temperature from the inside of the pipe to the outside of the pipe. You don't lose as much heat. Plus, it's a highly insulated thing, right? I'm not going to be melting the snow on my campus. At Smith, we estimated that we were losing about 40 to 50% of our energy in distribution. 40 to 50%. That is such an incredibly big number. It's probably much lower here at Tufts for a variety of reasons. But in a lot of places, it's not. And that's how we know. Okay, simultaneous heating and cooling is a big potential if you can get it. That's the other big energy efficiency. If in fact you do a ground source system, then you have to balance that system. So now this comes back to your question, Ida, about managing the system. When you push heat all summer into the ground, you actually warm up the ground. The great thing about that is I can pull that heat out again in the wintertime. So the ground is now acting a little bit as a battery. That happens in most places. That's what would happen here. There's other places where there's a lot of groundwater and that doesn't happen. But here, you would actually be warming up the ground and then you'd be cooling it off. You have to watch the temperature of the ground because you don't want to freeze it. Because if you freeze it, that would be bad, right? Then you've frozen your system. So you watch that and you model the system and you make sure that it's balanced so that all that hot and all that cold are in check over the course of a year. Everybody with me? For some campuses, that means you need to add cooling load. So for the price of decarbonizing your campus, you can add air conditioning. So places like here at Tufts, where we have a lot of buildings that aren't air conditioned, and yet the ambient temperatures are getting warmer, there might be a beneficial synergy between adding air conditioning and decarbonizing the system. There's the potential for reduced water use. Most complexes, airports, campuses, hospitals, the #1 use of water is cooling. It's evaporative cooling. We've got big chillers to make things cold, and we're keeping that equipment cold by evaporating water. When you get to know what they look like, it's just like a big box with a big fan. These things are everywhere. And it's the single largest use of water in the United States is cooling, mostly for big power plants. But it's an incredible use of water. When you cut that out, because now I've got a hot water loop and a cold water loop, and I've got a place to dump that extra heat, now I saved a lot of water, and I'm not putting domestic water into a evaporative cooling system.
Also, anytime steam's leaking out of the steam system, you have to put water back.
Yeah, that's right. Right. I need makeup water for all these like steam leakage. So at Smith, it was about 13% of our total water load was in evaporative cooling, and about 6% of our total water usage was in makeup water for the steam. So these are like very big numbers, millions of gallons. Okay, and then last, when you cut out your gas plant, although it's regulated, you're still making particulate and low-level ground, right? You're still making oxides of nitrogen. You still have ground level pollution. So when you cut that out, you're actually you're benefiting everybody's health, right? On your campus and in your community. All right. So I wanted to just mention a few other places where this is relevant. This is not just relevant to college campuses. On the left, this is the city of Vancouver, British Columbia. They have a district system that uses the sewer as their heat recovery system. So this is called the False Creek Energy Plant. And they heat and cool 15 mid-level urban buildings. So this is a pretty high density urban setting. And they basically, the heat pump sits next to the sewage line. It's a really big sewage line. And they extract heat from that sewage. It doesn't go into the buildings. Everybody stay calm. But it's a great source of heat in this environment. This down here is a pilot program, Eversource pilot program in Framingham, Massachusetts, where they're looking at creating a district system for a residential neighborhood. So it's a way that the gas utility can change their business model to one that is decarbonized. Now they're running a loop of water and running heat pumps in homes. So that's the Eversource model. NYSERDA, which is the New York State Energy Research Agency, is doing a similar thing in Albany, New York, and actually across the state of New York. So there's all these interesting pilot programs that are pushing a lot of really great information about how to design these systems that are happening all over the country and like literally right here in our backyard. So that's kind of awesome. All right, so what are we doing? Let me just talk about one last district because it's particularly complicated. This is our Boston campus, for those of you who don't know it, right? This is the dental school. This is the med ed building. This is Jaharis. This is the biomedical research complex, right? Big buildings in an urban area. And because they're mostly laboratory buildings or clinical buildings, they are highly ventilated. right? They're pushing a lot of air through these to keep the air clean because of what's happening in the building. Well, that uses a ton of energy, right? Because I gotta like reheat, recool, rehumidify, redehumidify all that air that's going through those buildings. I don't have a lot of space for things like ground source heating and cooling. So these are complicated. There's a question about how do you actually mechanically electrify big buildings like this in an existing high density urban neighborhood. I think this is a complex question. They are on a district system, interestingly. It's a steam system. So this is a map of downtown Boston. Our campus is kind of here. The lines are just the steam lines. So there's a steam utility. They're making steam in Cambridge, piping it at high pressure across the river, all through this system. And it uses, right, there's a huge amount of waste in that system. And the steam's really expensive. And the condensate, once the steam gives up its heat, the condensate doesn't go back to the plant. It just goes down the sanitary sewer. So it's incredibly water consumptive. So this is a big thorny thing that's on our radar. All right, so planning status at Tufts, just so that everybody here knows, and then we'll come back to Emma's question. We made plans for the Grafton campus and for the Medford Somerville campus to decarbonize, to electrify. They involve lowering the temperature of water distribution, doing renovations to buildings, and really using air source as our medium for heating and cooling those buildings. That planning was done before the Inflation Reduction Act, and I cannot tell you how dynamic a world we are living in right now. We have new federal legislation. We have a new Massachusetts Climate Act. We have new local law. We have a new local law in the city of Boston, probably one coming in the city of Somerville, that are like carrots and sticks for doing all of this work. So we're stopping and we're going to replan what's happening here in Medford and Somerville and in Grafton, because the Inflation Reduction Act gives a lot of money for ground source heating and cooling and no money for air source heating and cooling, which had been our plan. So we need to just go back and take another turn. And it's so many different systems that it actually sort of it's a replanning exercise. So that's where we are right now and thinking about our own systems. That is actively work underway. And we're going to complete a plan for the Boston campus. So that's all part of what's happening. We've got a team that's working on it, and we're talking to students and faculty about how to do that work. So that's kind of my quick overview. Now, Emma, remind me what you asked about.
I have two questions.
Okay, awesome, go.
The first one was just looking at geothermal for Tufts. I couldn't quite get a sense of how big that field was that you were looking at, and whether it would look like 4 or 6 like deep bore wells or like a more shallow configuration.
So here's the thing with geothermal. It's these are all like optimization problems. So we need a certain amount of capacity of it's a surface area problem, like under the ground. So if you are going to be serving a certain amount of heating or cooling, you need a certain amount of surface area under the ground. So you have choices. I can either drill more wells over a bigger distance, or I can drill a smaller number of deeper wells. And usually, your engineering planning team kind of figures out where you land on that. So I can tell you at Smith College, first we were going to drill 600-foot deep holes, but then we realized, well, the demand's going to be a little bit higher and the space is a little bit smaller, so we're going to drill 850-foot deep holes. When you start getting down to 1,000 feet, the economics start going upside down. So there's something about drilling more holes is more expensive until they get to a certain depth, and then they start getting really expensive. And so there's this cost and optimization problem that you're constantly working on with these kinds of systems. It's cheaper and easier to go straight down. There are systems at Carleton. They have a vertical system, which is the one that I had the photograph of. They also have a geofield that's in a river bottom. And when they tried to drill down, there was so much hydraulic pressure under the ground from the groundwater, the water was just coming out of the earth. So they built a horizontal field, which seems to be working pretty well for them. Apparently it's not quite as I think it's an efficiency question or it's a cost efficiency question. That it doesn't work quite as well. So they kind of look at wells first. You also have to have like a really big, like a well, like I could put one well here and I can put another well over there. It's a little bit easier. So that's the story on that. Did you say you had another question?
Yeah, my other question was just related to local laws. Do you know of anything in the pipeline for Medford that Tufts is gonna have to accommodate, like anything like Budo or Birdo, as you're looking at like electrifying the campus?
Yeah, so the question is anything coming down the pipe in Medford?
Mhm.
Nothing specific that I know of. Somerville, on the other hand, so remember the whole lower campus is in Somerville. So the campus center and DeWick and Pearson Hall, right? And all those dorms, that's all in Somerville.
Mhm.
And Somerville is looking at BERDO, which is the Boston regulatory scheme for energy use. Somerville is looking at that. They want to make it one better than BERDO. They want to, Somerville wants to one up Boston. So we'll see what they do. But that's something we are talking to them. Tina and I just had a call with somebody from the city of Somerville to say like, oh, what are you thinking? Like, will you involve us? Because they tend not to think about the thing that I worry about, okay, in the cone of silence, right? So the thing I worry about is the municipalities, when they think about it, is they think about it on a building by building basis. And we work on a district basis. And so if they say, well, if they pass something that's like gonna make it really expensive for us to have to renovate one building, that's actually becomes cost inefficient for us because we could decarbonize a lot of buildings in a less costly way. So I just want to make sure they're thinking about us. I don't know how a Somerville regulation would consider the fact that we're making all the energy in Medford. I got a lot of questions. So there's some presumably all of this stuff is a one-way ratchet. So all of these sources of CO2 emission are going to be further and further regulated everywhere, I hope, right? And then Medford will follow along after Somerville at some point. I have not heard anything specific to suggest that they would do so.
Yeah, they told me they would.
Oh, Tina says they are, so there it is.
Yeah, I mean, I don't know, I haven't seen anything.
Yeah, we haven't seen anything yet. But other questions? Comments?
Why does the city of Somerville look at buildings on a building by building?
That's a good question. I think it's because when you think about the urban form and the development in the city of Somerville, it's mostly individual buildings.
Owned
So-
by individual people.
Yeah, owned by individual people, and even where there's like higher density or like, it's almost all residential. So if you're a policymaker in the city of Somerville and you're like, okay, how do I do this? And you're saying like, well, 95% of my city landform is covered by 1, 2, and 3 family houses. I'm going to be thinking my regulatory framework is going to be towards that kind of development pattern. And they're not thinking about like, well, Tufts University, well, they have a district system, and we're not on their radar. So we sort of need to put ourselves on their radar, not because we don't have aligned policy goals. Our policy goals are totally aligned, but they could write something where we'd be like, no, wait, can we just do it this way? So that's my policy concern.
Tufts help. They talk to Boston, like we talk to Boston a lot about BERDO. Wasn't doing counterintuitive incentives.
Right, and this is like the policymaking process for anything, right? I'm trying to solve a problem. I've got all these different constituents and special interests. How do I kind of like pull all that together in a meaningful way?
What is the policy that you mentioned?
BERDO, it's what does BERDO stand for?
Boston Energy Reduction Disclosure and Ordinance. Disclosure Ordinance.
What Tina said. What it does, more importantly, is it's a fee that's being imposed by the city of Boston on individual building owners. They are saying you have to hit a particular energy target for the total energy use in your building. And if you don't, you have to pay.
A lot.
And it's essentially a carbon target. So I can, if I buy, let's say I buy renewable electricity for my electricity supply, that comes off of my energy use budget. And so I can get under that regulatory threshold that way. So it's sort of like a carbon fee imposed on real estate in the city of Boston. And then they do it by use, right? So if you run a hospital, if you run a dental school, you get more energy that you're allowed to use than if you run a home. That makes sense? It's kind of complicated, and the kinks are still being worked out of it, but it's very interesting at as a national policy model, super interesting.
And the Mass Climate Act actually also included sort of the groundwork for at least the reporting and disclosure portion of that statewide. So nobody knows if the actual limits will come next, but
right. So what Chris is pointing out is, right, we have this new Mass Climate Bill, and we have a new governor who has a new climate chief who is looking at all of the executive agencies, and we don't actually know what's going to happen from that, but we do know, for example, there are regulations pending for something called the Alternative Portfolio Standard, which would potentially pay someone like Tufts credits or money if we moved our fuel sources from gas to ground source heat exchange, for example. But that's still in play. So we don't know what it's going to say yet. So complicated.
This is a kind of like maybe controversial, but like I remember when I was at Tufts, we still have the old power plant.
Mhm.
Now we just got a new power plant relatively, and now we try to move to the more sustainable energy, green energy way. So do you think that's the investment that we kind of lose in the new power plant because we're trying to go into this more renewable energy approach?
Yeah. So I think what Lee Chen was asking is about, like the power plant in the picture that I showed you, that's fairly, what is that, like 2017? 2018, right? It's a pretty new piece of equipment. It costs a lot of money. It does some neat things. It makes electricity as well as heat. It makes electricity and heat in the same cycle, which is a much more efficient way to provide electricity and heat to campus. So that's all cool, right? That's actually an improvement, but it's still a fossil fuel asset. So I think the trick is, and this is why, right, the forward planning is complicated, right? Because what we need to say is we have that asset, it's going to run for a little while, and we're going to we need to make some decisions, or at least set some targets about when does that reach end of life? When does that asset go from producing electricity all the time to now it's an emergency backup and resiliency measure, which is actually really important when you have a system that's entirely run on electricity, is if you can make a lot of electricity on site, that's how you get your resiliency. Because otherwise, especially if you're a research university, you have problems. So that asset's actually really important to us. But what we need to do is figure out how to use it less often in the future and sort of figure out at what time in the future that ends up being. It's a great question.
And it's also the hub of a distribution system, which unless we switch away from, district energy, we're still going to need distribution.
Any other questions? Yeah, Chris?
I know you touched a little on the Boston campus and
Yeah.
the district's team there. What are your thoughts on the vicinity energy green steam or e-steam plan?
Okay, so here in Boston, I mentioned we have a steam utility. This is something that's common across kind of the northeast part of the US, right? There's a steam utility in New York and Philadelphia and Baltimore, and I think they're all owned now by the same company, Veolia, which is a French conglomerate. And the local company is called Vicinity. And they have introduced something they call green steam or e-steam. E-steam. And the joke is that the E stands for expensive. They are rightfully, and I actually appreciate the fact that they are trying to find ways to decarbonize the production of steam. It's really hard to do, right? Boiling water is a really energy intensive activity. And it takes a lot of fuel to do that. To do that with electricity through an electric boiler is really inefficient, right? It takes a lot of electricity to do that. So it means that the steam price is going to get more expensive. but their livelihood kind of, right, they've got a problem with Birdo because they're a pretty fossil fuel intensive source of energy right now. It's getting less so. So I think what they try and do is they're thinking about like preheating some of that water with a heat pump up to a point, and then they take it from however hot you can get it there to boiling using electric boilers. And they've kind of got a plan, but we're concerned that A, they're the only game in town, and B, that it could be very expensive. And that they see opportunity to make it very expensive because Birdo is the alternative.
To follow up on that, I think that their big goal is to tap into the offshore wind.
Yeah.
So that's ultimately they'll get there, but then it's the big if, how fast offshore wind comes.
Yeah, right.
It doesn't, then it's gonna get.
So the plans for offshore wind, you probably know this, right? So plans for offshore wind, massive in New England, like could provide 40–50% of the electricity demand in New England. Question is do we want it to go into like an inefficient process like boiling water to make steam, or do we want it to go into other stuff? And I think that's a major policy question. But yeah, I think that's exactly what they're looking towards, and probably they're trying to sign some like very favorable contracts to do that.
It's interesting.
It's super interesting. And I think it's an interesting question at the heart, right? I'd rather have them boiling water with electricity from wind than not, right? From a climate standpoint.
And it's a speed question too, which you talked about earlier about efficiency. And they point out that all of those buildings that are heated by steam now, the time and expense it would take to get them converted to those flat panel radiators,
It's mind-boggling. And a lot of those buildings like ours it's much more complicated than just radiation because they're big laboratory buildings, which are complicated mechanically. So it's rough. Okay, there are people coming in. I'm thinking maybe it's a class. Come on in. No big deal. But we'll wrap up there. Thanks, everybody.